Now let's talk about collecting a gas and how it's done. And mostly, especially in Gen Chem classes, but a lot of times, mostly collecting gas is done in lab over water. And this is what an experimental setup might look like. If we're doing the reaction of zinc solid, which is shown down here, in a solution of aqueous hydrogen hydrochloric acid, the reaction, and this should be an arrow, not a question mark, produces hydrogen gas and aqueous zinc chloride. And the hydrogen gas then creates bubbles, and you can bubble that gas through a glass tube, collect it into an upside down beaker or other glass container. And when you do, the gas that's here is hydrogen, but it's also got some water vapor. And the water vapor comes about because there's water creating the lower surface for the collection, and some of that water evaporates. And it's a little hard to see, but some of these molecules are hydrogen molecules, H2, and some of them are water molecules. Now, the overall equation is that P total, sometimes called P lowercase t, also called P atmospheric, because it will show that it is the atmospheric pressure pushing down on it, is going to be equal to the sum of the partial pressures of the gases inside here, which is going to be partial pressure of hydrogen plus partial pressure of H2O. And since it's a pressure, it is H2O gas, and sometimes we note that and sometimes we don't. So the pressure in here is, so the two partial pressures add up to the atmospheric pressure, and the pressure inside here, just like related to a barometer, we saw that the atmospheric pressure pushes down here, and there's no atmospheric pressure in here pushing down. The only pressure created in here is by the gases that are collected here. Now, both of these gases have the same volume, which is the volume of the gas, and so we just refer to that as V, and they're at the same temperature as well. Okay. And so what will happen is we'll be able to measure the atmospheric pressure. Now let's talk about this partial pressure of H2O, where we get that, and then we'll be able to solve for the partial pressure of hydrogen. Now the partial pressure of the water vapor, called the vapor pressure, depends only on the temperature. And let's define vapor pressure, because vapor pressure comes up at a couple points in this course. The vapor pressure is the pressure or the partial pressure of a gas in contact with the liquid. So just like in the picture we've got here, we've got liquid water here, and we've got water vapor, or H2O gas, up here. And vapor pressure is a completely general and a very useful concept in a lot of different instances. However, we're going to be using it principally for H2O and H2O pressure. So whatever the temperature is, you can see that the pressure or the vapor pressure depends on it. And in fact, one thing I'll point out here is that at 100 degrees Celsius, which is the boiling point of H2O, the vapor pressure is equal to 1 atmosphere, which is usually the atmospheric pressure. And so one definition of boiling is the temperature at which the vapor pressure equals the atmospheric pressure. So the note we want to write here is that boiling point of H2O is when vapor pressure equals atmospheric pressure. And when the atmospheric pressure is lower than 760. 760 is the atmospheric pressure and is equal to 1 atmosphere at sea level. So as you go to higher and higher elevations, the atmospheric pressure decreases, and then the vapor pressure equals the atmospheric pressure at lower temperatures. Okay, so let's see what a problem like this looks like. 1.02 liters of oxygen collected over water at 293 Kelvin with a total pressure of 755.2 millimeters of mercury. Find the mass of oxygen. So let's see. We have a total pressure, PT, equals 755.2. And that's in millimeters of mercury. The total pressure is going to be equal to the partial pressure of oxygen plus the partial pressure of the H2O, where again, the partial pressure of the H2O is on the previous slide in that table. And we'll look that up now. So 293 Kelvin, subtract 273 from that, and you get 20 degrees Celsius. We come back to this table right here. We see at 20 degrees Celsius, the partial pressure, or the vapor pressure, is 17.55 millimeters of mercury. And rearranging to solve for the partial pressure of oxygen, we subtract 17.55 off of the 755.2. So, and to 3 sig figs, we'll just go with 738 millimeters of mercury. And 738 millimeters of mercury, well, when we're going to find the mass of oxygen, we're going to then put that into the ideal gas law, solve for moles first, and then find the mass. And to do that, we need atmospheres. So I'm just going to straight away convert my millimeters of mercury into atmospheres. And using 738 divided by 760, I get 0.971 atmospheres. Okay, so we've got our partial pressure of oxygen, we've got our volume, and we've got our temperature. That's enough information to solve for the moles of oxygen using the ideal gas law. Here's the ideal gas law in general, and this will work fine. I like to personalize it when we're using a specific gas so that the pressure, or the partial pressure of oxygen, will be specifically for the moles of oxygen, although those are, well, let's see. If we're using the partial pressure of oxygen, we will get moles of oxygen. And then go ahead and plug everything in. R is the ideal gas constant, 0.08206. And temperature 293 Kelvin. And rearranging to solve for my moles of oxygen. Let's see, so it's going to be these two divided by these two times 1.02 divided by 0.0206 divided by 293 equals 0.0412 moles of oxygen. And from there, we need grams of oxygen. And 1 mole of oxygen equals 32.00 grams. Times 32 1.32 grams of O2. And that's a very typical problem using partial pressures, using vapor pressures and total pressures. Okay. This is going to be a companion problem, similar, except this time we're working to find the total pressure, and that's a good place to stop for now.